minus x squared over the square root of 16 minus x squared equal to 0. So this step 1 right here, just to refresh your memory, we are trying to find the critical numbers, right? That's what we're doing. That's what this step is. We're trying to find these critical numbers, so we're trying to figure out where the derivative is 0. So we got to set that to 0, and we've avoided this for a long time, haven't we? We've avoided trying to work with these expressions. I just wanted the raw derivatives, but now we get to test your algebra. So how can we solve that equation? Common denominator first, right? You always want to try and get the left side to be like just one fraction. So I'll look at this as being over 1, multiply top and bottom of this by root 16 minus x squared over root 16 minus x squared. Okay, so at this point, what we know is that the new line, the denominator will be a common denominator of root 16 minus x squared equals 0, right? And then on the top, I do this and this together, right? And the 16, you just get the 16 minus x squared. But then we have minus x squared again. So it'll be minus 2x squared. And I talked about this last class, this very important thing to notice now. You have a fraction equals 0, right? Right? A fraction equals 0. So the only time that can happen is if the numerator is 0. So all I have to do now is just ignore this and just look at the top and set it to 0. That's the whole reason we put them together, okay? Right here, when we're at this point, when we set this to 0, you cannot just set the top to 0 because it's not a single fraction. When you get it to a single fraction, then you can set the top to 0. So now, setting the top to 0, the numerator, right? We're setting 16 minus 2x squared equal to 0, and I'm hoping everyone's comfortable solving that. So just moving things around, isolating x squared, and then taking the square root on both sides. You must do plus or minus. Okay. 2 root 2 if you want. How about as a decimal? 2.828. Okay. 2.828, 2.83. We're round. It doesn't matter. Get it pretty close. So we're approximately plus or minus 2.83. Yeah? Okay. Now at this point right now, you can check to make sure if these both live inside your interval, or you just need to remember to do it later. So I just remembered it right now, so I'm going to do it right now. Which of these answers, they could both be in our interval, and they could both not be in our interval, or one could be and one's not. So I forgot our interval. What was it? -1 to 4? So that negative 2.8 is gone, right? So the only thing that I'm going to take from this is x is 2.83. So far, I have one critical number. 1. Am I done with step 1? No, I need to see where the derivative is undefined, right? I need to see where the derivative is undefined. That's my second thing here. So where's my derivative undefined? Oh, defined. So I erased my derivative, but I'll put it back up here so we can look at it. Our derivative was square root of 16 minus x squared over square root of 16 minus x squared, right? So what about that? Is that ever undefined? We know that that's the original function, right? Or no, the original function is, the original function was x square root of 16 minus x squared. And we were on the interval -1 to 4. And we said that pretty much this function is well defined on this interval because we never get a negative under here, right? I said the worst case scenario we get is what? If we plug 4 in there, then this thing becomes 0, right? But the square root of 0 is just 0. So it's not a problem here, right? But over there it is. Because over here, if x is 4, what happens? That's division by 0, right? So we actually have a critical number here of 4. and greater, right? Anything greater than 4, but we are still only allowed to look here. So even though 5 doesn't work also, I mean, there's an infinite number of numbers that don't work, we're still just looking here, but the thing is 4 is actually in here, right? So 4 is a critical number. So now what we need to do is we need to plug these critical numbers into the original function, right? And see what comes out. Then we're going to plug the endpoints into the original function and see what comes out, and we're going to compare them. Do you all see that one of our critical numbers is our endpoint? So we don't have to do it twice. We just have to do it one time. But I just want to make sure that you get the 4 from this, right? You can't miss this. Okay, because sometimes that critical number that comes from that part is not in there, or not one of the endpoints, I should say. All right, so now I'm going to continue this step. I'm going to evaluate my original function at 2.88. Or you know what? I'm going to do it. Yeah, I'll do it. Well, whatever. 2.83 is what I meant to say. And then I need to evaluate my function at 4. I'll do 4 because that's the easy one. That's 0, right? Plug in 4, you get 0. And then plug in 2.83. So that's going to be root 8, root 8. Is it root 8? Root 8?
Yes, it is.
So it's just 8? Okay, you just get 8. I went back to the original. Remember when I did this right here? I went back to this right here. We only really had the positive answer there. So I just plugged in root 8 right here. And then root 8 squared is 8, and 16 minus 8 is 8, and root 8 is root 8. So root 8 times root 8 is just 8. Okay. For me, it was easier to work with the exact answer than the decimal there. All right, we're not done, right? Step 2, test the endpoints. So at the endpoints, I actually only need to check one of them, and that's at -1, because I've already checked 4. So f of -1 would be, it's -1 times square root of 15. So negative root 15. And of our 3, now how many answers do we have? We have 3 answers, don't we? We have this one, we have 8, we have 0, and we have this one right here. Of those, I think it's pretty obvious. This is your global max, and this is your min. You could write them as ordered pairs now, right? It's the min because it's the smallest, right? Smallest meaning negative, not smallest meaning closest to 0. Smallest meaning on the number line furthest to the left. Or on the graph, it would be the furthest point down. Well, what do you think?
Shouldn't 8 be between, shouldn't you look at it?
Root 8. Are you saying, is root 8 between here and here?
I was looking at the max. Max of 8?
Yep.
Should it be between -1?
No, because this is the output, not the input.
So that's why.
The y value. This is the x value. So if we graph this, I think that's a graph we don't see every day, right? X times the square root of 16 minus x squared. There's the graph. And we're just looking between -1 and 4. So right here, -1. Right, and is that right? Yeah, that's negative root 15. See that negative 3.87? That's negative root 15. That happened at -1, and then we have a max up here at 2.828, which is what we got, right? And the max value is 8. Yes, yes, yes. Oh, how? Oh, the brace? Crap, man, really? And then what? -1, less than or equal to x, less than or equal to 4. Thank you. There we go. I knew I had done it before. Thank you. All right, so there it is. That's it restricted. All right, let's try a new one. Okay, how about this one? Same instructions. Find the global max and mins of x squared times e to the negative x on the interval -1 to 3. So now, I mean, as you can see, just the functions are going to start to become tedious, more tedious to take derivatives and set to 0. That's all that's going to happen now. And when I say that's all, I mean like that's all. Like it is going to be a bitch. Like it's not going to be fun as we proceed because the algebra is going to start getting really complicated. Am I allowed to say that in 2019? I don't think I can. Well, I probably offended somebody. I'm on this thing about offending people. I really just can't stand the world right now. Everybody's so sensitive, you know. I'm trying to harden my daughter up a little bit, you know. She has things happen. I'm like, you know, come on, suck it up. All right, so first thing, I'm going to take derivative. I got to make sure it's continuous on the interval that I'm looking at. If it's not, then I can't do the method, right? So it is a continuous function. How do I know it's continuous? This is continuous, x squared by itself, right? E to the negative x is an exponential function. And it looks like, well, not like that. It's reflected. It goes like this. It's decay. And that's continuous. And when you multiply two continuous functions, you get a continuous function. So we can proceed. So now I will try and find the critical numbers. So the first thing I'm going to do is take the derivative. Let's go ahead and just take the derivative. Let's just get used to taking the derivative, all right? The derivative of this function is going to be another product rule, right? Unless you want to drop the e to the x down. If you want to drop the e to the x down to start the problem, we could do it like this and do a quotient rule with a positive exponent on x on the e. Your choice. I'll stick with the original. Okay, this is 2x times e to the negative x. Drum roll. Plus negative e to the negative. Okay, so everyone okay with that part? Now I'm supposed to say plus, right? I'll do plus, I'll do it a little bit slow. Plus derivative of e to the negative x is e to the negative x itself times the derivative of what's up here, -1, times the x squared. Okay, so if you mess up the derivative, it's over, right? Like it's over at that point. So we have to be very proficient and careful with this. And also I should note that where we're headed is not only are we going to be doing this, taking the derivative and setting it equal to 0 and figuring out where it doesn't exist, we're going to be doing the exact same thing with the second derivative also. So we have to be able to do the first derivative and run this test, and then do the second derivative and run this test again. And so if you mess up the first derivative, of course your second derivative is done then, right? Okay, so now let me just try and clean this. 2x e to the negative x minus x squared e to the negative x. Is that right? Yeah? Okay, that's actually not as bad as it looks because we're going to need to set that equal to 0 now, right? So if I go to set this to 0, and from now on I'm going to just start writing this. Instead of f prime of x, I'm just going to write, okay, f is being set, the derivative is being set to 0. So here we go. Derivative is being set to 0. 2x e to the negative x minus x squared e to the negative x equals 0. How would you go about solving that? Factor out an x and e to the negative x, right? Just greatest common factor. So pull out an x, pull out an e to the negative x. What are you left with inside when you do that? Just 2 minus x, right? 2 minus x. And the whole idea behind factoring is that if you can factor something and set it to 0, then all you have to do is just set each factor equal to 0, right? Just set each one equal to 0. So I have 3 little equations I'm going to look at here. First, x is 0. The next one is e to the negative x equals 0. And then the next one is 2 minus x equals 0. So all 3 factors set to 0. The first one is just x is 0. How about e to the negative x equals 0? You could do natural log to get your x, but think about it. Think about the graph of that function. This is e to the x, right? E to the negative x is this, right? So is this function e to the negative x ever 0? It's never equal to 0, right? So that has no solution. There's no solution to this. Jackson, I heard you say infinity or something like that? That's if we were doing a limit, right? But this is actually an equation. We're just trying to figure out if there's an answer to it, and there is no answer. There's no solution here, okay? And then this last one, x is 2. Right? So far, we have 2 critical numbers. Maybe a quick check. Are these in our interval? They're both in the interval. That means they both get to be checked. Okay, now, next thing I need to do is figure out where the derivative does not exist or is undefined, right? If you want to put does not exist, that's fine, okay? Maybe in my homework solutions I say figure out where it's undefined or figure out where the derivative doesn't exist. Pretty much the same thing. So take a look at your derivative, which is right here. Are there any values of x that would cause problems with that? Well, I mean, that you're never going to have a problem there, right? You're never going to have a problem there. The only issue you might have is with e, but we already said e to the negative x looks like this. Like there's nothing you can plug into e to the negative x that's ever going to cause a problem. It's defined everywhere. So we have no issues with that. Nothing from that. And now we plug these answers into the original function. We're going to plug 0 in, and we're going to plug 2 in. And we plug in 0 into the original. To the original, that means this. We get 0 squared times e to the negative 0. And that's just 0. Because what's e to the negative 0? What's e to the 0? 1, right? 1 and then times 0 squared. Don't be thinking like 0 times infinity L'Hopital. Don't be thinking that because we're not doing limits right now. We're actually plugging numbers into things, right? So that's 0. How about 2? Plug in 2, we get 2 squared times e to the negative 2, which is the same as 4 over e squared. So 2 squared is 4, and then e to the negative 2, I dropped it down, e squared. And then I could get that as a decimal, and it will be approximately 0.54, 0.54? Okay. So here are my outputs, right? Those are my output values so far. I'm getting 0 to come out. I'm getting 0.54 to come out. What's next? We have to check the endpoints now, right? We've checked the critical numbers. We've seen the outputs. Now we need to go to the endpoints and check the endpoints. And these endpoints, this is really like step 2. Okay, step 2 is to plug in the endpoints. So I want to know what f of -1 is. I want to know what f of 3 is. F of -1 means -1 squared times e to the -1, which really comes out to just be e. And then when I plug in 3, I get 3 squared e to the -3, which equals 9 over e cubed. So I know that e is approximately 2.718, but I'm not quite sure what 9 over e cubed is. 0.45? Approximately 0.45. So the things that we're comparing are this one, this one, this one, and this one. Those are the things we're comparing, right? The outputs from our critical numbers versus the outputs from our endpoints. So step 3, I guess we'll put our final answer here. The global max and the global min. If I were doing this for, what is the global max going to be? The E? Yeah, if I were doing this, I would write -1 E. I wouldn't do the decimal, because that is the exact answer. That is the correct exact value. And then for the minimum, 0, 0. 0 in, 0 out. That comes from that one. Okay? All right, we need to do another one. Trying to see how bad we want to actually go here. Okay. Okay. Yes. Oh, is that the stack? Thank you. Did y'all want to see the graph of that one, or can I just move on? Okay. What's that?
Can you graph it, please?
I can. While I graph that, I'd like for you to consider the following. Where was it? I just had it. There we go. 2 cosine x plus cosine squared x. And I want us to look on the interval 0, 2 pi. I'll graph the previous problem, and then we'll do that one. So the previous one was, what was it? X squared times e to the -x. There it is. And we were on the interval -1, 3. Okay, so there's the graph right there. Okay, there it is. So we found the max to be at -1, right? E, which is this point. That's -1 E. And we found the minimum to be at 0, 0, right there. Do you all agree that that is correct? Looks good, right? Looks like we found the lowest value right here and the highest value right here.
This is one of the things you can't do on the calculator, right?
Is what?
It's you can't do that on the calculator, right?
Do what?
The graphing, like find the graph. On the,
You can.
you can.
To find the max and mins? You can't.
Okay.
Yeah.
I don't know why I stopped because like my graph has a little bit whether I zoom in or zoom out, to see the whole thing.
Yeah, but there's actually a built-in function in the calculator that will go and find it for you. Like not where you go and guess. Like it goes and gets it. Which if this were a class on using your calculator, we would do that, but it's not. But it's a good way to check. It's a good way to check. I wish that we could have a class where everyone is required to have a TI-89 or something like that, where all the calculus can be done with the computer, and then we would do like real crazy good stuff. The problem is requiring a $150 calculator isn't going to go over very well. Yes?
That's fine. I was just curious, like, when was it that they allowed students to use calculators for exams? I know it wasn't always like that.
Yeah, I don't know. I mean, some point. Well, even now, I mean, there's people who don't. Like, I won't allow you to use a TI-89 because it can differentiate and solve equations and do everything, pretty much. All right, here we go. Is this a continuous function on a closed interval?
Yes.
No. Have we had this discussion? I want to make sure we are clear on this. Have we had the discussion about why we still need to learn how to do this even though the computer can do it? Have we had this discussion? Okay. So let's have a brief discussion on this. What happened? I thought you just... Oh, okay. All right. So, how do I explain it? Okay, so when I was in school, okay, as a math major, took a course, I don't remember if it was a junior level or senior level math course called numerical analysis, all right? And we had a project that we had to do that was due at the end of the semester. And the project was this. We had to go find 3 commonly used mathematical software platforms. There's a bunch of different ones out there. So engineers like to use certain things, and everyone uses kind of to solve math problems, right? So I had to go pick 3. I picked MATLAB, Maple, and Mathematica. Those were the 3 programs that I chose. And so the task was this. I had to go find a function that was built into the software. All right? I had to go find some built-in function, and I had to go look at the code for that function and see how the code worked. And then from that, I had to find a weakness in the code. And so the project was to do this. Feed this function a problem, okay? So I would come up with a problem, whatever it was, solving something, where theoretically, with pure mathematics, I could show the answer. Okay? But make the function give me an incorrect answer. So basically the output of this was wrong. Right? So analyze the function, find a weakness, exploit the weakness, give a wrong answer, prove theoretically the right answer. I had to do that for 3 different platforms, right? The moral of the story is this. You're an engineer, you're whatever, right? You're out there building a bridge, building an airplane. You're going to use software. You're going to use it, okay? And you're going to trust it. Like right now, if I go to Wolfram Alpha and I type in solve, I trust it's going to work, right? But there's nothing at stake. I'm standing in a classroom, right? I trust that answer, but who cares if it's wrong, right? We all go on with our day. Planes don't fall out of the sky. So this project was called, I think it was called like the black box, okay? What happens if we become too dependent on calculators and we start teaching at this level how to use your calculator to do calculus? Then this black box becomes the black box for everyone. And the only people who know how it works are the people who are programming it, right? And so you're getting answers and you're hoping those are right. And you're building planes and buildings and everything else based upon an algorithm that might have weaknesses. Somebody has to understand the theory behind everything. Like you have to have a foundational theoretical basis for everything. Because the machine will make mistakes. All machines will round. At some point they will round. And that's usually the way you can exploit them, is by using that rounding and making it compound on itself, if that makes sense. So you have to remember that this is a math class. Like, you have to have this class for engineering, you have to have it for computer science, you have to have it for this and that. But I always try and approach this from the framework that this is still math. Like, math is about the pureness of math, not, do I really need this? I'm going to use a computer one day to do it. I still have to come at it from that point of view that we need the people that understand the box. Does that make sense? Okay, so I realized we could do a lot of really cool stuff if we had a computer in here. We could do really cool calculus, and I hope that's what you'll do later. But the foundation has to stay, in my opinion. All right?
Did you ever find all the holes?
I did the project right, yeah. I was able. I mean, the weaknesses are there. The hardest part was getting the answer theoretically. Like, you could find the weakness, but then you'd realize, oh crap, that means my problem has to look like this to exploit that weakness. How am I going to solve this without the computer, right? Yeah.
So I suppose in the project it would have been important to identify also the magnitude of the failure. Like, to what level of, how catastrophic could this failure?
Okay, well, the one I did, I can remember one of them was solving systems of equations. So most, like a matrix, right? So you put in this thing, you solve a system of equations, gives you the solutions. That's the one I exploited. So I mean, that could be part of something that's used, Yeah, I mean, it depends on how that's being used, but yeah, I mean, that's a pretty big deal, right? And they get better. These algorithms get better. So once they find somebody is like, okay, there's a weakness here, then they'll tweak the algorithm. If the input is looks like this, then we're going to change the algorithm to handle that sort of scenario. I mean, it's a back and forth always, But you got to have someone who understands the algorithm. All right. Continuous? Yes? No? It's continuous because cosine's continuous. This is continuous because you square continuous, you're still continuous. All right, let's do derivative because we're going to need it. You know what sucked about that class? What sucked was I wasn't a CS major. So I didn't have any real coding experience. And that's where I had to learn to code. Like, that's where I had to learn it. I had no choice. It was by default. I had to learn the language because I had to be able to exploit the language, right? So what is that called? Whatever. Okay, so this is this. 2 comes out, 2 cosine, then derivative cosine, which is negative sine. And that's our derivative, right? That's our derivative. Clean it up a little bit. Sorry, I'm thinking I want to change the interval. I do. I want to change the interval. Can we change this? Yes, thank you. Let's change it to 8 pi. Let's change it to 8 pi, 0 to 8 pi. All right, there's our derivative. What do we do with that derivative? Set it to 0, right? Set it to 0. So I'm setting that derivative equal to 0. Negative 2 sine x minus 2 sine x cosine x equals 0. And that equation should look familiar if you took pre-cal. It's called a trigonometric equation. And we solve trigonometric equations the way we normally solve other equations. We do factoring and all that stuff still on the table. So everyone see what we can factor here? You can pull a negative 2 sine x out of both. I always tell my pre-cal students that the 2 things I want them to come out of pre-cal with, if there's anything they need for sure, it is you better know your unit circle. And that doesn't mean know where it is in your folder. Okay, that means know it. And then the other thing is you better know how to solve trigonometric equations. And it's because of where we're headed right now. Trig equations are just going to start showing up in random places now. So we want to be able to solve them. So we factor this out, and now we set both factors to 0. So I set negative 2 sine x equal to 0, and then I set the other one, 1 plus cosine x equal to 0. Now what about that first equation? That negative 2 I can just get rid of, right? Divide both sides by negative 2. So this is really saying sine x equals 0. And then this one, if I move things around, is really saying cosine x is negative 1. And now here comes the pre-cal. And this is also why I changed my interval. What is the solution to this equation, or solutions to that equation? Where within the interval 0, 8 pi does sine of that angle equal 0? Is that in hand? Where at?
Each factor of pi.
Any multiple of pi? Any multiple of pi or 2 pi? Pi. Okay, so let's just run through that real quick. Visually, this is how I do it. This is how I teach my pre-cal. I draw a unit circle. Sine is always the y-coordinate. The y-coordinate being 0 would happen here and here. So that's 0, that's pi, that's 2 pi, 3 pi, 4 pi. So any multiple of pi. Okay, all the way up to 8 pi. So my solutions for this are x must be 0 pi, 2 pi, 3 pi, right? All the way out to 8 pi. Now in pre-cal, a lot of times when we had general solutions, we would put something like, like n pi or k pi or something like that. But here we're actually stopping. So I'm just going to list them out. Okay, all the way from 0 pi to 8 pi. Now how about over here? Where's cosine of x equal to negative 1? So cosine is the what coordinate? X coordinate. Where's the x coordinate negative 1? Just here, right? That's the only place where the x coordinate is negative 1. So this is going to happen when x is equal to, let's see, pi, and then we have to go all the way back around. So 3 pi. So this is going to happen at pi, 3 pi, what's the next one? 5 pi and 7 pi. Now, all of these are inside of our interval, and so now we need to plug those into the original function and check them. And I'm almost out of time. So here's my original function. There is some good news on this, all right? Because it's going to be pretty easy to evaluate these because they're all going to give you the same values for sine. So if we go back up here, what's f of 0? Well, 0, what's cosine of 0? 1, so that's 2, plus cosine of 0 is 1 then squared, right? So 1? Y'all agree? So what's that? 3, okay. Now at pi, what's happening? So now, what's cosine of pi? Negative 1, so this is going to be negative 2 plus negative 1 squared, which is positive 1. So this gives you negative 1. So what's going to happen at 2 pi? Same thing that happened at 0, right? Because 0 and 2 pi are the same angles, basically. The same terminal point. So this is also going to be 3. What about at 3 pi? It's the same thing as what's happening here, so that's going to be negative 1. So is there anything that's going to be different? So yeah, what about at 4 pi? 4 pi is the same as here. 5 pi, 6 pi. And these answers are included in those, aren't they? So there's only 2 outputs coming out of these. 3 and negative 1. 3 and negative 1, right? Questions? Now what do we need to check? The 2 endpoints. But aren't the 2 endpoints in here? The 2 endpoints are in this list, right? So we kind of already are going to check them. So what's the global max? 3, and the global min? Negative 1. I'm out of time. We'll have more practice with this. For now, what I'd like for you to do, I mean, we're pretty much done as far as the theory of this section. You can do your homework for 4.1. Yes?
How would you rate that,
How would you write?
the answers for this one?
So this is one of those situations where you have the max occurring at a bunch of places. So you'd really just state what the max is. And then if you wanted to, you could break it down as a bunch of ordered pairs. On a test, I don't see me giving you a problem where you would have like 8 different places. Maybe it would be 3, so it wouldn't be that bad to list out just the 3 ordered pairs. All right. Do your homework for this section 4.1. All right. And have a good weekend. Have fun tonight. Be safe. Get crazy. Let it go.
I was in math 2